ZKProof picture. It's going to be right before lunch. So make sure to comb your hair. You'll see, you won't be able to miss it. It's, I think, downstairs, like floor 0. And also all the hotel guests won't be able to miss it.
Yeah.
Okay, so I'm very happy to have an invited talk from Norbert from Gevulot. At some point we'll need to understand why the word Gevulot, because it has meaning for some of us in the crowd. You're going to be talking to us about
how to start proving on Gevulot.
Exactly, and it's a demo, right?
Actually, I'm only having slides, but it's going to be kind of practical, trying to make it like that.
Okay.
So that.
Thank you. So Gevulot is a network to actually create proofs, and we're going to see how to practically use it.
Yeah, trying to make it as practical as possible. Hi everyone, I'm Norbert, and I'm doing protocol research at Gevulot. So I'm not a cryptographer. It's awesome what you guys are doing and building, and what we are building at our end is a platform where you can easily deploy any arbitrary proof system as an on-chain program and easily generate proofs on a performant infrastructure at a low cost and in a decentralized manner. So that's the TLDR. So a little bit about why decentralization matters, and I think Ben mentioned it yesterday. Also, the Aztec team has put out a pretty nice blog on it on their forum just a couple of days ago. There's been a lot of back and forth around it. So the problem statement, our problem statement would be, the proving market is susceptible to centralization, and we don't want to replicate what can be seen in Web2 cloud computing. And because of that, we feel it's very important to create a network that can actually legitimately compete with any centralized solutions out there. So one of the key questions regarding design considerations would be, how do you allocate workloads, and what mechanisms do you use to allocate proof requests? There are different approaches to this. Auctions is one of them. However, for example, the Minas marketplace shows that prover undercutting is a reality and happening today. I don't know if you are aware, some entities started offering proofs there for free. And this actually killed the whole economics and the whole competition on this marketplace. There are obviously easy measures to go around it, but just want to point out that prover undercutting and like some entity underbidding others to gain monopoly could easily be in the cards, and it's a reality. On the other hand, proof racing, where it's kind of like proof of work, everybody racing to generate the proof, but only the first one getting rewarded, that's another mechanism where resourceful entities could easily become dominant, so to say. And obviously there are a whole bunch of other mechanisms, for example, randomness, which is much more neutral and can offer much more fair allocations, but I won't go into details now. What does a higher risk of centralization mean? As I mentioned regarding auctions and proof racing, this is reality and a real risk to be aware of. It brings, or it can mean, increased liveness risks, higher centralization risks, and losing the properties such as permissionlessness or trustlessness. And these, like the decisions that you need to take when picking where to have the proofs generated for your proof systems, actually has implications and may come with different trade-offs that it's worth to be aware of. The core values around, like, why are decentralization-focused design decisions important, and what do they give us? They ensure that no one can control where proving happens. They ensure higher liveness guarantees and censorship resistance. it brings about a trustless environment, a fair distribution of workloads and rewards, and all this boils down to credible neutrality. And like at Gevulot, we believe that the ZK future, we believe in a ZK future where proving is cheap, performant, and decentralized. And that's the vision we've been building ever since from day one. So just in a nutshell, we offer a full-stack ZK cloud. We have proving, verification, and a bunch of customization being built in so that you can work with data availability or data storage solutions or even external dependencies, external software dependencies. You can plug in TEs, FPGAs, ASICs, like any exotic hardware easily, etc. We'll talk in detail further down the line in a sec. So, in a nutshell, basically, we are a decentralized proving layer optimized exclusively for ZK proving and verification. We are aggregating workloads from all over the industry, and this adds up to us being realistically orders of magnitude cheaper than the current solutions out there, like AWS or Web2 cloud solutions. The network is very performant because it's exclusively optimized for proving and verification, so very minimal network. We don't even host smart contract state. We have hardly any re-execution. I'll talk about that a bit later as well. And we are flexible because basically you can permissionlessly deploy any arbitrary proof system on Gevulot as an on-chain program. We support different languages. Also, there is support for multi-threading, GPU proving, etc. And we'll talk a little bit more about that as well. So, we are a programmable blockchain that allow any arbitrary proof system, as I mentioned, to be deployed as a prover program. It basically means that anything that can be compiled into an ELF binary and then wrapped into a Nanos unikernel image can be easily deployed and run on Gevulot. And we'll talk about this as well a little bit later. But coming back to programs, programs on Gevulot come in two varieties. You can deploy provers and verifiers. And actually currently on our live DevNet, which I'll show some stats about, you need to deploy them together. The blocks in Gevulot include transactions as in proof requests, or, for example, program deployment transactions, and proofs. So as I mentioned, no smart contract state, no re-execution there. The two main network actors in Gevulot are the validators and provers. We are having, as I mentioned, a very lightweight underlying blockchain. It's Comet BFT-based consensus built on the Cosmos SDK. Very lightweight, and it serves the purpose of being able to manage and distribute workloads and rewards in a fair and efficient manner. So validators process transactions, broadcast workloads to provers, form consensus on block content and replicated state. There is a randomly selected leader for every round and for every block, and they are responsible for ordering transactions into and proofs into blocks. And there are the normal incentives that you would expect for validators in other networks as well. For provers, the main tasks are obviously proof generation, but in Gevulot, a subset of provers is randomly selected again to validate every single proof. Participation for provers is staking based. Oh yeah, actually that's the same for validators. So we want economic security to be there behind. And we do capacity verification for provers. Initially, upon joining our network, they are assigned a couple of random workloads which they need to complete within some time constraint. And we do periodic random verification as well, just to make sure that they are constantly capable and available to generate proofs. As I mentioned, proving tasks are randomly assigned to a prover. They need to accept or decline each and every task. The decline function is there because we don't want to punish provers who have some ad hoc constraint. Honest provers who have some ad hoc constraint. It will be limited because we don't want this feature to be spoiled, but we will allow them to have a couple of decline cards, so to say, every month or every week. So in case a prover accepts the workload, but they don't deliver, a fallback mechanism kicks in where a new round of random selection comes and the proving workload is reassigned. But also users are given the opportunity to customize redundancy. So for example, worst case scenario that can happen is your workload is initially assigned to a prover that does not deliver. Then it's reassigned to another one who delivers, and it's 2x the initial time that you were expecting it to be generated in. If you cannot wait because of your use case, you cannot afford waiting 2x the time, you can add additional redundancy and make sure basically the fallback mechanism is not even triggered. So a quick overview on the life cycle of a proving workload on Gevulot. So as a user or a proof requester, you send a transaction to the network to request a proof. The receiving node adds this transaction to the mempool. It gets included in the next block. Once the transaction has been included in the block and finalized, by the way, we are looking to have like sub-second block time, so that shouldn't add much latency there for like in general. So it's randomly allocated to a prover node. The prover node generates the proof, sends the proof back to the mempool. The proof is included in a block and becomes available for verification. But at this point, I need to mention if some use case or the user is doing settlement on another layer, they don't need to wait for us to verify the proof. It's important for us to verify it internally, because based on that, do we pay rewards to our provers. But if you settle your proof on Ethereum or any other solution, then you can already make use of it at this point and don't need to wait for the rest to come. So the proof gets included in a block. The randomly selected subset of prover nodes for validating that proof or verifying that proof will see it's available there. They vote on validity. Once everyone has voted, it gets the verification result itself gets included in a block. It reaches finality, and then we pay the rewards to the provers. Like in a nutshell about economics. Proving fees consist of two components: a small transaction fee, mainly to prevent spam, and then a compute fee. The compute fee, the user needs to specify resource requirements for the proof request or the prover workload, and also needs to specify the maximum compute time up to which the program should be run by the provers. And based on that, we will calculate the fee for the user. There is something we call a user fee rebate, which could be the longer the user has to wait for their proof, the more rebate they get out of the initially calculated fee. So basically, in other words, the longer it takes for the provers to deliver the proof, the lower the reward they get. And this is important because we want to incentivize provers. Like, we believe in positive incentivization. They earn more if they are faster. So that's what we expect them to optimize for in general. And we are building something which we call custom prover sets. Basically, nested within our global prover set, you can create custom sets with custom prover programs. The use cases for this could be, for example, as I mentioned already, plugging in specialized hardware, integrating specialized hardware, or if you want interoperability with other blockchains or data availability or storage solutions, or you just have some external software dependency, you can connect to those through these custom prover sets. For example, one thing which is a practical example, we are working close to the STAC team, and in order to generate the aggregate proofs for STAC, we need to have the full state of STAC. And we have two options. Our prover nodes could run full nodes on STAC, or we get that piece of necessary state through custom prover sets. So this is also another use case. Participation for provers in these custom prover sets is voluntary, but we will do additional verification, making sure that whatever is needed to be able to successfully generate a proof for the custom prover set and the custom prover program, they have that and they meet those requirements. A bit about the technical aspects. Communication between the external programs and the prover program is happening in a virtual isolated network within the Gevulot node. We allow flexibility in configuration using different interfaces and various protocols. Service discovery can be automatic through MDNS, or it can also go through passing config details through the task definition, and all this, like maintaining security and integrity of the network, is very important. So that's why these things. Regarding pricing for custom prover sets, it's actually the deployer of the custom prover program that will define the price. There will be a minimum cost to prevent like something that happened in the Snarket place, for example. And regarding network rewards, yeah, I think I didn't mention it at the economics. On top of the user paid fees, there are network rewards paid to the provers. And in case of custom prover sets, by default, there is no subsidy, because it could happen that you deploy a custom prover set and you allow only one single prover to do proving for your custom prover program. So in that case, we don't want to subsidize that. However, proportional to the percentage of the global prover set participating in the custom prover set, we are paying the network subsidy as well. And then this is the more practical part. So we launched our DevNet on the 25th of March. I think it's almost exactly 2 months ago. It has the full proof generation pipeline already up and running. So it means you can already come in and deploy any arbitrary prover and verifier. You can run proving workloads, generate proofs, have them verified. You can track workload status, etc., etc. It's already up and running. Currently, it's a permissioned DevNet, which means certain node operators are taking care of running the nodes, but it means in return that it's free for all registered users. It's going to be up and running for the next couple of months, and we already have teams who use it for benchmarking, for example, because instead of renting racks or like servers on AWS at a very high cost, actually we have quite beefy servers as well. So you can feel free to try it. We appreciate any feedback you can give, and this is basically free proving to support the community now. We have a live dashboard that's, I think, from yesterday or the day before yesterday. We generated almost 900K proofs in the past 2 months. Verifications are higher because we verify on multiple prover nodes. We have a couple of prover programs pre-deployed, like more known ones, like the Tyco ZKVM prover from the previous testnet. We are working on the current one. We have the Starknet Stone prover pre-deployed, working on the Polygon ZKVM prover. Also other larger ones. And actually, there was a ZK hackathon last weekend in Krakow where one of the devs working on our bounties deployed the RISC-0 ZKVM also on Gevulot in about, like without any support, basically in a couple of hours time. So that's something recent. You need to generate a key through the Gevulot CLI and then have it registered. We allow list it in a couple of hours or in a day or two max. But if you drop me a line, we can speed that up. And very easy to register and generate the key. A little bit about prover and verifier integration. So the running environment is a Nanos unikernel, which basically provides a very lightweight operating system. It can be, basically the images can be spinned up in a couple of milliseconds without adding additional latency. As I mentioned, there are a couple of requirements. For example, the program has to be compiled or has to be compatible with Linux x86 architecture. So you need to be able to compile it into an ELF binary. But we have a shim library which we created. It's written in Rust with C bindings, and this is to facilitate simple integration. For example, for a Rust implementation, you have two small modifications to make: a callback function to be added and a new main function to delegate control to the shim. We have full detailed examples and code snippets in our docs under docs.gevulot.com. Packaging, as I mentioned, our programs are running in a VM under the Nanos unikernel, so there has to be a manifest file containing the configuration data on how the program should be run. And then there is, you need to install ops that is working with Nanos to compile and to build, to compile the program and to build the image that can be booted, the bootable image. Also, on our docs, we have very detailed examples and code snippets regarding this as well. And the final element is the actual deployment. Once you have your key registered and the CLI installed, you need to calculate the hash for the programs for integrity verification. It's important. You need to upload the programs, both the prover and the verifier, into a public HTTP server, and then you deploy it through the CLI. A couple of useful things that are worth mentioning. As I mentioned, currently the deployments go hand in hand. Provers and verifiers need to go together, while in the future probably we will allow standalone verifiers to be deployed as well if you want to have proofs generated outside Gevulot being verified. You need to define resource requirements for your prover. I mean, there is a default resource allocation in case you don't want to consider that, but you can customize it and basically specify how many cores, how much RAM, etc. should be allocated to your program when our nodes are running it. And again, the full example and all the details are worked out in the DevNet. And yeah, I think this is my last slide. Currently, we are on the far left. The DevNet is up and running. We are starting a mainnet in about a month or 5-6 weeks. A mainnet level, let me put it this way: a production-grade DevNet, a permission network which can already serve mainnet use cases. We are onboarding node operators now for that.
Is it true to say that if I get a proof from the testnet, it's a proof, right?
Yeah, obviously. So currently, even on the DevNet, you deploy a program, you get a proof, and it's a legit proof. So what we do is when you send a run transaction, you need to specify the hash of the program that you want the input to be executed on, and then our prover nodes will actually spin up the image, spin up the program, take the input, execute the proof, or generate the proof, and then send it back to you. So these are actual, well, these are not like toy proofs, these are the actual proofs if you've deployed your own proof system, and they can legitimately be used, settled, etc. And actually that's how the idea of the Firestarter came about, because teams have seen that these outputs and proofs generated on Gevulot are already, like, they create value, and they were asking, can you actually prove our mainnet or our testnet? And hence we started off focusing on, okay, how can we make the DevNet kind of production and like mainnet ready, while we are working on our incentivized permissionless testnet Deluge coming in Q3, and then our mainnet ZK Cloud coming in Q4, probably November, December-ish, something like that. I think this is it from my end. Check out our website, check out our docs, docs.gevulot.com. And yeah, we are open to any feedback, we have a dedicated TG channel or TG group for developers who already joined the DevNet, and we are constantly providing basically live support there to help you integrate easily. Yeah, thank you very much. Thanks.
So a blockchain is normally a way of sequencing transactions that need a total order. Given that proving and verification are stateless operations, so given that you've set up a given VM, why do you need those to be on-chain?
Very good point. Actually, we want a network that can... Yeah, so we want, in order to have credible neutrality, we wanted to... Okay, let me put it this way. So in order to be able to control and make sure that we have a random selection, we have a fair distribution of workloads and rewards, we have all the economic structure worked out the way it is, we felt it's better if we have an underlying blockchain that can process all these. We are not dependent on any other one. I would also say we are kind of ecosystem agnostic in that sense, because we send the proof back to whoever requested it, and then they can use it in whichever ecosystem. For us, we felt it's better if we have these proofs and like the finality after the proof has been verified, etc. And also the proofs are being stored on Gevulot as well. So we felt it's a more robust network, so to say. I mean, I don't know if this answers your question, but like these were the considerations. If we were to launch it as, let's say, an L2 on Ethereum, then it's hard to become credibly neutral towards Solana or any other ecosystem users, because you know what I mean. So we consider different elements, and the same thing, if you run it on or deploy it on Solana, then again, it's hard to... Anyway, we didn't want to get aligned with one single ecosystem, but more be aligned entirely with the ZK space and generate or provide some platform that can give you guys cheap and performant proofs.
Yeah, I'm just thinking that the witnesses and the input data are potentially very large.
Yeah.
Other questions? Okay.
It is about the design choice for the underlying blockchain. Why did you go for a Cosmos SDK? Because you were mentioning decentralization. From a validator perspective, it will be around 100, I guess. Because also you mentioned Mina. They went for, I think, Ouroboros, which is allows, like, I think, a much more participation from a validator perspective. Was it because of the deterministic or the probabilistic finality? You were making this trade-off because of that? Just want to know.
Mm-hmm. Thank you very much. Yeah, as I mentioned, as a protocol researcher, probably I'm not the best suited person to answer that decision, but we've looked into different solutions or different, like for example, we considered Avalanche, we looked into others as well, and because we don't want much added latency due to our block time, like considering a sub-second block time already kind of narrowed down our choices, to say so. And yeah, that's a good point, because you look at DYDX or you look at some other chains built on the Cosmos SDK, which have sub-second finality or sub-second block time. They're validator set does need to be constrained in a way, so it cannot be thousands of validators because you will have such a networking overhead that it's not gonna work. That is something that we took into consideration and had to make a trade-off there. We'll have, I don't know, 100 or a certain number of validators needed there, as many as we can, to make sure we can still fit into the desired block time. On the other hand, for the provers, like hopefully random selection and some other mechanisms built in will ensure that it's safe and safely operating even with 100 validators, let's say. But regarding provers, we expect thousands and thousands of provers to come online. I mean, we've done some research on how many provers or what proving compute capacity some rollups would need to have their current mainnet, let's say, proven. And yeah, we are talking about thousands of prover nodes. So in that sense, the proving side will be enormously decentralized, and we'll make sure that the validator side will be as decentralized as it can, but it's still much better than I don't know, going with AWS or any other centralized entity.
Okay, thank you very much.
Thank you.
Norbert.
Thank you for having me.
So if you go back to